All right, so the topic for today is chapter 4.6. We're looking at the multiplication rule for independent and dependent events. So if we're looking at independent events, probability of A and B, we're just multiplying the two probabilities. One event does not influence the other event, so each event is entirely independent. When we're looking at it for dependent events, here probability of A and B is the probability of A times the probability of B given A. So in these scenarios, one event does influence the other event. In order for both events to occur, the first one must occur. So just a reminder that this notation here, that conditional probability, reads as B given A. So for B to occur, A must have occurred first. All right, I have a bunch of examples ready to go. Here we go. So first, on January 28th of 1986, Space Shuttle Challenger exploded on takeoff, killing all 7 crew members aboard. Afterward, scientists and statisticians helped to analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Experts estimated that the probability that an individual O-ring joint would function properly under the cold conditions that day was 0.977. But there were 6 of these O-ring joints, and all 6 had to function properly for the shuttle to launch safely. So assuming that O-ring joints succeed or fail independently, that is crucial. Find the probability that the shuttle would launch safely. Okay, so first I'd like to define what do we deem success versus failure. So success, that an individual O-ring joint would function properly under the cold conditions of that day, is 0.977. So for one event to be successful, that chance is 0.977. Failure would be its complement. So 1 minus 0.977 would be 0.023. Okay, so the shuttle would launch safely. That means that all 6 O-ring joints function properly. Okay, so what does that look like? So the first one, there's a success, 0.977. So is the next one, 0.977. So is the next one, 0.977. And we do that so that we have all 6 of them. Now it's just a little bit faster to type that in with an exponent. So 0.977 raised to the 6th power, which is exactly what I'm going to do. Okay, so if I type in 0.977, I need to raise it. So I use this caret button right under clear caret to raise it to the 6th power, and then I hit enter. So it gives me as a decimal 0.8697. Right, I've shown you before how you can round it to 4 spots. So I can do mode. Go down from where float is, go to 4, enter, and that tells that you want 4 spots. So if I try that again, 0.977, caret raises to the 6th power. Now it rounds it for me. So that's my answer in decimal form. I will take it as a percentage too. If you give it to me to 2 percentage points, that's fine. All right, so then if I say the shuttle would not launch safely, what does that take? Right, that takes at least one of them fails. So So at least one fails, right? Which means that it could be one fails, two fails, 3, 4, 5, or all 6 fails. It just takes one. So here, I think it's a lot easier to go through the complement. Complement being that 0 fail. So 1 minus the probability that 0 fail. None of them fail. So here, if zero failed, that means that they were all successful. Which we've already solved for. So 1 minus 0.8697, right? That was the launch that went smoothly. So here we get about 0.1303. So that was the likelihood from the get-go that the shuttle would not launch safely, 13.03%. All right, so as a result of this analysis following the Challenger disaster, NASA made important safety changes to the design of the shuttle's booster rockets. All right, more examples. So find the probability of flipping a coin and obtaining heads in all 4 tosses. Now this scenario is completely independent. Right? Coins have no memory. They don't know what happened prior. So I'm looking for 4 heads in a row. So first flip, I have a 1 in 2 chance of it landing on heads. Next flip, that probability stays the same, 1 in 2. Third flip, same deal, 1 out of 2. Fourth flip, 1 out of 2 as well. So if I multiply this across, I get 1 out of 16. Okay, next situation. Assume that 26% of the population has a certain non-threatening life disease. Find the probability of randomly selecting 3 people at random and all have the non-life-threatening disease. Okay, so here, I guess we're probably being redundant, right? We've said random twice, so we can just say random once. Let's do that. All right, so regardless, I need to think, is this going to be an independent situation or is it dependent? Well, when we're talking about the population, right? So if I'm talking about the population of like Americans, right? That's 332 million people. If I was talking about our world population, we are at 7.9 billion. So one rule that we have to abide to here, we just underline population, is that if our sample size is less than 1% of the total population, we deem it to be independent. So let me write that in our notes. So if our sample size is less than 1% of the total population, we deem it to be independent. Okay, so if our sample size is less than 1% of the total population, we deem it to be independent. We don't think it's going to be very impactful if we remove one person from such a big population. It's not going to change those probabilities very much. Tiny little bit. All right, so same thing here. I'm going to flesh out what I think is success versus not. And it doesn't have to have positive connotation. So here's success, like whatever I'm told in the situation, that's someone who has the disease. So has disease is 0.26. All right, then the complement of that, right, does not have disease. So I'm just fleshing out what my 2 options are here, right? You can have it or not have it. One is the complement of the other. So here in A, if I say that all have the non-life-threatening disease, right, we're saying the first person has the disease, so does the second, so does the third. So 0.26 times 0.26 times 0.26. Right, I'm just going to type in 0.26 and raise it to the third power. I've already told my calculator to round it to 4 spots. So 0.26 caret to the third power. And here we get about 0.0176. And as a percentage, 1.76%. Okay. How about if I say at least one person has the non-life-threatening disease? So here, that would be saying that it could be 1, 2, or all 3 have disease. All right, so it might be easier to go through the complement, which is 1 minus the probability that 0 have the disease. Okay, now I haven't solved for that, right? Because here, what I've solved for is they all have the disease, not none of them have the disease, but I can calculate that because that would be saying the first person, 0.74, that would be the chance of not having the disease. Same with the second and same with the third. So I can do 1 minus 0.74 to the third power. Okay, so let's say that I calculate 7.74 to the third power first. Make sure I'm getting this all on the same screen. 0.74 raised to the third power. Okay, so this is like saying 1 minus 0.4052. So 1 minus, second negative is my previous answer, and we get about 0.5948. Again, I've told my calculator, please round to 4 decimal spots. So 59.48%. Okay, I have another one. Very similar. If you wanted to try this on your own, you could. So next up, suppose 42% of the U.S. population loves cats. If you select 3 people at random, find the probability A, none love cats. So again, we're looking at a big population, right? U.S. population specifically, 332 million. So we're going to say this is independent, right? Because my population is so big, if I pull a few people from it, it's not going to make a difference. So here, if I flesh out again, what are my 2 options, right? Love cats, 0.42, or don't love cats, right? Do not love cats. That would be the complement, 0.58. Okay, so if I say none love cats, that means that all 3 of them do not love cats. So no love for cats. Let's see, well, how would I want to write that? We'll go no love for cats. All 3 of them. Okay, so that means I'm taking 0.58, right? No love for cats. Same here, and same here. And then I'm going to write that as 0.58, raise it to the third power, and then multiply across. All right, so 0.58 caret third power. There we go, 0.1951. So 19.51%. That would be my chance of all 3 having no love for cats. Okay, and then if I say here at least 1 loves cats, that means it could be exactly 1, 2, or 3 who love cats. Okay, and again, might be easier to just go through the complement, remove the 0 option. 1 minus the probability that 0 love cats. And this time I have already solved for that right up here. So I can say 1 minus what I've already solved for. 0 of them, none of them love cats. So the 0.1951 figure. So if I do 1 minus that, I get 0.8049, or 80.49%. So you'll see that sometimes there's scenarios where we can easily build off of the previous step, and sometimes we have to solve from scratch. And I gave you one of each of those in example 3 and example 4. So this one I could not build off of what I had previously, but here in this one I could. Next example. All right, so far I've given you all examples that are deemed independent. Now I'm going to give you one of each. So here I'm saying find the probability of drawing 3 consecutive face cards from a standard 52 card deck with replacement. So if I'm replacing, then my events are totally independent versus without replacement. Here it is dependent. Right? My probabilities will change because one event does influence the next. Okay, so scenario A, with replacement. So I'm saying face card, face card, face card. So first pick is a face card. I have 12 out of 52. Okay, I put that card back in the deck. I replace it. I draw again. My next pick is a face card. Still 12 out of 52 chance. I put that card back in the deck. I draw again. My probability for the third face card here in a row is 12 out of 52. So again, if I type that in, parentheses, 12 out of 52 times 12 out of 52 times 12 out of 52. There we go. It's going to give it to me as a decimal, but I'm going to say math frac. Turn it into a fraction. So I get 27 out of 2,197. Okay, what does it look like without replacement? Right, again, dependent now. So face, face, face. So first pick is still the same probability, 12 out of 52. But now I'm not putting that card back into my deck and I'm drawing another face card. I now have one less face card and one less card total. So now 11 out of 51. I again do not put that card back in the deck. I draw again. One less face, one less card total, 10 out of 50. So when I type this in, 12 out of 52 times 11 out of 51 times 10 out of 50. Enter. Math frac. Here we go. 11 out of 1,105. Okay, let's flip it over. Let's go to the back. All right, so here I have a box containing fuses, 4 of which are defective. 2 fuses are randomly selected. The first one is not replaced before the second selection. Make a tree diagram to summarize the possible outcomes. Calculate each probability. Okay, so if we look at what this could look like, we could get a fuse that's defective or not defective. We draw again, could be defective or not defective. All right, so these are really all the scenarios that could unfold. So if I visualize each of these pathways, so first defective, defective, 4 are defective. So I'm looking at 4 out of 15 are defective. That's my first pick. Next pick, I'm picking another one that's defective. I'm not going to pick the same one twice because this is going to be a dependent situation. Right? One outcome affects the next. We're not replacing before the second selection. So now I have 3 that are defective out of 14 total fuses. And if I multiply this across, this gets me 2 out of 35. Okay, next pathway, defective and then not defective. So first one being defective is still 4 out of 15. But now we're picking one that's not defective. So if we have 4 that are defective, we must have 11 that are not defective. So I still have 11 that are not defective, but I have 1 less fuse. Multiply that across, simplify, and we get 22 out of 105. I'm just reducing my fraction to make life easy. All right, next pathway. I start with one that's not defective, so must be 11 out of 15. Right? I don't replace it. I draw again. Now I have 4 that are defective, but 1 less fuse, so out of 14. Multiply across, simplify that fraction. I get 22 out of 105 again. Okay, last pathway, 2 fuses that are both not defective. So first draw, I have 11 out of 15. But now I have 1 less non-defective fuse, so 10 here. 1 less fuse overall, 14 here. Multiply it, reduce it, 11 out of 21. Okay, just a reminder again that whenever we see a situation like this, all of these probabilities, they have to add to 1. Right? They represent all of the possible options for what could play out, so they have to add up to 1. So now I'm just filling in the blanks, and the first 4 are pretty easy because we've already calculated them. So both fuses defective, that was that first pathway, so 2 out of 35. Both fuses are not defective, that's this pathway, so 11 out of 21. First fuse is defective, but the second one isn't. That was that second pathway, so 22 out of 105. The first one is not, but the second one is. That's this pathway. Same probability as the previous one, so 22 out of 105. So then when I ask you this, at least 1 fuse is defective. That means it could be 1 or 2 that are defective. So that means it could be this pathway where I see 2, this pathway where I see 1, this pathway where I see 1. So I could add up all these probabilities to get to my conclusion. That's fine. That works. I can do that. But maybe easier to go through the complement. Remove the pathway that has 0 fuses defective. That's the easiest one. So 1 minus the probability that 0 are defective. So if I do 1 minus 11 over 21, I get 10 over 21. Okay, a few more examples and we're done. I think 2 more examples, then we're done. All right, example 7. There are 40 painters and 25 sculptors attending a conference. If 3 are selected at random to display their work, find the probability that all of them are painters. Okay, so we're picking 3 at random. We're picking 3 different individuals, so this is a dependent situation. Right, I'm not picking the same person more than once. So I'm picking 3, and they are all painters. So I'm picking a painter, and then a painter. So we have, it's just good to keep in mind that we have 65 total artists in this scenario. So first pick is a painter. I have 40 painters out of 65 total artists attending this conference. Next pick, I'm not picking the same painter, so I have one less painter and one less participant, 64. Next pick, I have one less painter, one less participant, right? So I'm seeing how my probabilities are changing from stage to stage based on having one less person to pick from. So if I plug this in, right, I'm looking at 40 over 65 times 39 over 64 times 38 over 63. Okay, there it is as a decimal. Let's do some math frac, and we get 19 out of 84. Okay, so what if I say none are painters? That's the same thing as saying, well, they must all be the other option. They must be the sculptors. So I must have a sculptor, sculptor, sculptor. So we have 25 sculptors out of 65 total participants. Next pick, also a sculptor. I'm not picking the same one, so one less sculptor, one less participant. So 24 out of 64. Last sculptor, I have one less sculptor, one less participant. I have to multiply that out. So I have 25 out of 65 times 24 out of 64 times 23 out of 63. Multiply it, math frac, and we'd say 115 out of 2,184. That is our chance of none being painters, which means all must be the other option, sculptors. I think I lost my L. There should be a little L there. Sculptors. Okay. Lastly, at least one is a painter. So at least one is a painter. What does that mean? That means it could be 1, 2, or 3 painters. Okay, well, that's a lot of work. I don't want to solve for all those individual probabilities and add them up. I'd rather take the easier path. I'd like to go through the complement. So 1 minus the probability that 0 are painters. That none are painters, right? It means the same thing as saying all are the other option. All are sculptors. Let me get my L in there this time. All are sculptors. Okay, we already solved for that. I solved for that right here. So I want to do 1 minus 115 over 2,184. So I end up with 2,069 over 2,184. All right, one last problem to close it out. Okay, so internet sites, they often vanish or move, so that references to them can't be followed. In fact, 13% of internet sites referred to in major scientific journals are lost within 2 years of publication. Suppose we select 4 internet references from scientific journals. So find the probability that all 4 references still work 2 years later. Okay, so we're told that we have links that are lost or do not work. Right, and that figure is 0.13 if I look at that as a decimal. So that means that the complement, those that still work, must be 0.87. All right, so I'm looking for the probability that all 4 still work 4 years later. So we're saying they work, 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 and work. So I'm looking at 0.87, 0.87, 0.87, 0.87. Okay, so here we're saying that we're assuming that it's independent because we have such a big population of internet sites. So we're just going to multiply straight across, view it as 0.87 to the fourth power. So here we would get about 0.5729 or 57.29%. Okay, what's the probability that at least one of them does not work 2 years later? So again, that could be 1, 2, 3, or 4 are lost or do not work. Again, that's a lot of work. I'd rather go through the complement. So I'd rather do 1 minus the probability that 0 of them are lost, which is the same thing as saying that all of them still work. And I already solved for that, right? That's what I solved for up here. So I can do 1 minus 0.5729, which is about 4271. Or 42.71%. Okay, so lastly, explain why the calculation in Part A may not be valid if we choose 4 internet references from one issue of the same journal. Well, the issue is if we're using it just from the same journal, right, it's no longer an independent situation. Right, because there could be something faulty with just the journal itself. Maybe they took the whole journal down, right? So it's not really an independent situation if we're pulling from the same source. So here I would just tuck in no longer independent because it's the same journal. We're picking from the same journal. Right? It could be that the journal is no longer being published, so all of the links no longer work, right? So it's no longer necessarily an independent situation. All right, that's all I got. Have a good rest of your day.